Hello friends, I am back for the solid state part 4 lecture. In the previous 3 lectures, part 1, I discussed crystalline and amorphous solid. I discussed what is a space lattice, then the 7 crystal system, Breves lattice, and different types of cubic unit cell. In the second part of the lecture, I discussed the relationship between the radius of an unit and edge length of a cubic unit cell, whether it is a simple cubic unit cell or BCC unit cell or an FCC unit cell. Then also I discussed how to find out the atomic packing factor or packing efficiency, and we found that in FCC unit cell the packing efficiency was 74% compared to simple cubic unit cell it was around 52%, and in BCC unit cell it was 68%. Then in the part 3 lecture of solid state I discussed closed packing. I discussed what is hexagonal closed packing and what is cubic closed packing. Often we call it as AB, AB, AB type, and the cubic closed packing is called the ABC, ABC, ABC type. Then I discussed the different types of hole, the tetrahedral hole, the octahedral hole, the trigonal hole, and we found that if a crystal have n number of atoms, there will be both octahedral hole as well as there will be tetrahedral hole. So in a cubic closed packing, I have shown you that it gives FCC unit cell, and in FCC unit cell, the octahedral holes are present at the center of the unit cell and at the center of the edges. So today's lecture, I will be delivering a talk upon ionic crystal. So let us go to the PowerPoint presentation of solid state part 4 of this lecture. So solid state part 4, myself Vedanta Kumar Bora, Associate Professor, Department of Chemistry, DR College, Gulaghat. And you can contact me in my email vedanta69@gmail.com. Now, in our previous classes, we discussed the different types of crystal. It is an covalent crystal where the constituents are held together by covalent bond, for example, diamond, silicon dioxide. Then we have discussed molecular crystal, for example, ice, where the particles are held together by electrostatic attraction, which may be a hydrogen bonding or a dipole-dipole interaction or ion-dipole interaction or van der Waals interaction. So today we will be discussing ionic crystal, where basically the particles are oppositely charged ions and they are held together by very strong electrostatic attraction. So we already know sodium chloride. It is a crystalline compound and it is made up of sodium ion and chloride ion. So from this picture you can see that sodium ions are surrounded by chloride ion and chloride ion are also surrounded by sodium ion. Otherwise, what will happen? In an ionic crystal you have oppositely charged ion, so there will be a repulsion between cation-cation repulsion, and there will be a repulsion between anion-anion repulsion. And for the crystal to be stable, it is required that the attraction between the oppositely charged ion, that is sodium ion and chloride ion, is higher than the repulsion between similar ion, that is repulsion between sodium ion and chloride ion. So the ionic crystal will be stable only when the attraction is higher than repulsion. And this will be only possible if a particular ion is surrounded by oppositely charged ion. For example, a anion, it is surrounded by positive ion, and positive ion are surrounded by negative ion. Then only the attraction between cation and anion will be higher than the repulsion between cation, cation and anion, anion. In other words, I can say that in an ionic crystal, ions occupy hole. It may occupy octahedral hole, or it may occupy tetrahedral hole, or it may occupy trigonal hole, etc. Then only each ion will be surrounded by maximum number of oppositely charged ion, and the result will be the attraction between oppositely charged ions will be higher than the repulsion between same kind of ions. So in ionic crystal, there are no free electrons. So ionic crystals are generally insulator. In your higher secondary first year classes, we have already studied that why sodium chloride crystal is insulator, because there are no free electrons and the ions are held to each other by very strong electrostatic attraction, so they cannot move under a potential difference. So ionic crystal conducts electricity in solution or in molten state, because in solution or in molten state the ions become free, they get separated from their crystal and they can move under a potential difference. Now, general consideration, already I have told you that in an ionic crystal, the attractive force is higher than the repulsive force. And this is the general equation which gives you the measure of the force of attraction between two oppositely charged ions which are having charge Q1 and Q2, and this is often called as the Coulomb's law. That is, the attraction between two oppositely charged ions depends upon the product of their charges, where Q1 may represent the total positive charge and Q2 may represent the total negative charge. And the force of attraction is inversely proportional to the square of the distance between them. So when the distance between the ion is higher, then the attraction between the two ions will decrease. And this 1/4 pi epsilon naught, it is a proportionality constant, where epsilon naught is called the permittivity of the medium. Now what happens when two ions are infinite distance? Suppose two oppositely charged ions, let us say a positive ion and a negative ion, are separated by infinite distance. So there will be no attraction or repulsion between them when the distance between them is infinity. Infinity means very high distance between the positive ion and the negative ion. Now if these ions are brought closer, then the positive ion and negative ion will attract each other by Coulomb's law, and gradually their potential energy will decrease. So as the two ions come closer, the distance between them r get lowered, attraction will become higher, and whenever there is an attraction, there will be lowering of energy. So we assume that when the ions are at infinite distance, the potential energy is 0, because the ions are not attracting each other or nor they are repelling each other. So as they come closer, the distance between the two ions decreases, that is, the value of r decreases, the ions start attracting each other, and potential energy of the system gradually get lowered, and this is the minimum potential energy. And the distance between these two ions is r0, which is called the equilibrium distance. Now what will happen if you put these two ions closer than r0? If you put these two ions closer than r0, then instead of attraction there will be repulsion. That is nucleus-nucleus repulsion between the two ions and electron-electron repulsion. and repulsion always increases potential energy, and consequently potential energy of the system will increase. And when the ions are very close, then the potential energy should supply this. So this is the equilibrium distance R0, and the equilibrium distance is the minimum distance between the two ions where potential energy is least. So I hope this is clear to you all. Now, what type of energy that changes takes place during the formation of ionic compound? So for example, let us take the case of sodium chloride. Sodium chloride crystal contains sodium ion and chloride ion. So in sodium chloride crystal, sodium is present as the cation and chlorine is present as the anion. So in the first step, a gaseous sodium atom will lose electron to form a gaseous sodium ion. This process is called ionization of sodium. So in this step, energy is required to remove electron, which is called the ionization enthalpy of sodium, and it is equal to 5.14 electron volt. So a sodium atom in the gaseous state, when supplied with 5.14 electron volt energy, then the valence electron will be lost and it will give a gaseous sodium ion. Then in the second step, chlorine atom will gain an electron, and in this step energy will be released, and this energy is 3.62 electron volt. So first step, formation of sodium cation, the energy required is 5.14 electron volt per atom. Second step, chlorine atom is converting to chloride ion, so electron is added to the outermost shell of chlorine, and in this step 3.62 electron volt energy is released. Then sodium ion and chloride ion will come closer, and the minimum distance between them will be 2.51 angstrom, where potential energy will be least. And if we calculate the potential energy, it is seen that when sodium ion and chloride ion comes together to a distance of 2.51 angstrom, the energy is lowered by 5.73 electron volt. And this energy is a measure of lattice enthalpy of the ionic crystal. So for a pair of sodium ion and chloride ion to form one formula unit of sodium chloride, these are the energy changes. First step, energy is absorbed to remove electron from sodium. In the second step, energy is released when electron is added to chlorine atom to produce chloride ion. And in the third step, sodium ion and chloride ion come together through electrostatic attraction, and 5.73 electron volt energy is released. So ultimately, when sodium atom and chloride atom, obviously in the gaseous state, they form sodium chloride, then 4.21 electron volt energy is released, and this energy causes its stability. And higher the value of this energy, more stable will be the ionic crystal. Now, how an ionic crystal is formed? Already I have told you that in an ionic crystal, each ion, whether it is a sodium ion or whether it is a chloride ion, it is surrounded by oppositely charged ion. Then only the attractive force between oppositely charged ion will be higher than the repulsive force between cation or anion. So this arrangement will be possible only if sodium ion occupies holes of chloride ion or chloride ion occupies hole of sodium ion. Now, what type of ionic crystal will be formed? That means what will be the coordination number? So whether sodium ion will occupy trigonal void, then its coordination number will be 3. or whether sodium ion will occupy tetrahedral void, then its coordination number will be 4, or whether sodium ion will occupy octahedral void, then coordination number will be 6, or whether it will occupy cubic hole, then coordination number will be 8. It will depend upon the relative size of the cation and the anion. If the size of the anion is much larger than the size of the cation, that means the cation is very smaller in size than the anion, then the cation can easily get into the trigonal void. Then the radial coordination number will be 3. But if the size of the cation is higher, then it will not fit in the trigonal void. It may fit in the tetrahedral void or octahedral void or in cubic void. So what type of ionic crystal will be formed? What will be the coordination number? It will depend upon the relative size of the cation and anion. If the cation is very, very small, anion is sufficiently larger, then the cation will get into the trigonal void. Now, this radius ratio will determine what type of ionic crystal will be formed and what will be the coordination number, whether the trigonal void will be occupied or tetrahedral void will be occupied or octahedral void will be occupied. It will be determined by radius ratio. Radius ratio is the ratio between the radius of the cation and radius of the anion. So if radius ratio is low, value may be from 0.225 to 0.414. That is the radius of the cation to radius of the anion lies in this range, 0.225 to 0.414. Then the coordination number will be 4. That means the cation will occupy the tetrahedral hole or tetragonal hole. Now, if the radius ratio is slightly larger, it is in this range, 0.414 to 0.732, then it will not fit in tetrahedral hole because the cation is slightly larger. Then it will fit in the octahedral hole because octahedral hole is slightly larger than tetrahedral hole. Tetrahedral hole is between 4 units, octahedral hole is between 6 units. So definitely the octahedral hole is slightly larger or bigger than the tetrahedral hole. So in this case, when the radius ratio is between 0.414 to 0.732, the coordination number will be 6. That means the cation will fit into the octahedral hole. It will not fit in the tetrahedral hole. And if the radius ratio is high, the cation and anion are almost same in size, then the coordination number will be 8. That means they will be in the cubic hole, which is the largest form of hole, because cubic hole is formed by 4 units at the 4 corners of a cubic unit set. So the coordination number of in an ionic crystal and the type of ionic crystal, the shape of the ionic crystal, it will be determined by the radius ratio. So radius ratio very less, 0.225 to 0.414. It will fit in the tetrahedral hole. Coordination number will be 4. 0.414 to 0.732. Coordination number 6. And 0.732 to 1. Almost the cation and anion has similar size. Then coordination number will be 8. So these are different types of ionic crystal. X, that is sodium chloride. Sodium chloride. The coordination number is 6. Cesium chloride coordination number is 8. I will discuss this ionic crystal. Now let us first discuss the rock salt structure, which is called the sodium chloride structure. So for sodium chloride, the radius ratio, that is the radius of the cation to the radius of the anion, that is radius of the sodium ion to radius of chloride ion. Now sodium ion, it has got 2 principal cell. Chloride ion, it has got 3 principal cell. So sodium ion is smaller than chloride ion. Sodium ion, electronic configuration 2,8. That means outermost cell is 2. There are 2 cells, completely filled cell. Chloride ion, it is 2,8,7. The outermost cell is number 3. That is the M cell. So sodium ion is smaller in size than chloride ion, and the radius ratio of sodium ion to chloride ion radius ratio of sodium ion to chloride ion, it is 0.524, and 0.524 will be in this range from 0.414 to 0.732. It will be in this particular range. So the coordination number will be 6. That means sodium ion will be in the octahedral holes. So in sodium chloride crystal, chloride ion, because size of chloride ion is slightly larger than the size of the sodium ion. So the sodium ion can get into the holes of chloride ion. Chloride ion cannot get into the holes of sodium ion. For example, a deer can be trapped in between elephant, but an elephant cannot be trapped in between deer because the size of the elephant is bigger. So 3 elephants standing in 3 corners of a triangle can easily accommodate a deer in between them. So the size of the chloride ion is relatively larger than the size of the sodium ion. So in sodium chloride crystal, chloride ion undergoes cubic closed packing. Chloride ion undergoes ABC, ABC, ABC type of packing. So in cubic closed packing, you get an FCC unit cell. So in sodium chloride, chloride ion undergoes cubic closed packing, and it gives an FCC unit cell. And in FCC unit cell, units are at the corners. Here the chloride ions are at the corner, and chloride ion are at the center of each face. And the sodium ion occupy all the octahedral voids. And the octahedral voids are present at the center of the cubic unit cell. This is the unit cell. This is the FCC unit cell. This is the FCC unit cell. Chloride ion are at the corners, and chloride ion is also at the center of the faces. And sodium ion occupy all the octahedral voids, and the octahedral voids are present at the center of the unit cell and at the center of the edges. So a face-centered cubic area of cation with anion in all of octahedral hole. So chloride ion, it undergoes cubic closed packing, which gives an FCC unit cell. And in the FCC unit cell, chloride ion occupy all the 8 corners and the center of 6 faces of the cubic unit cell. And all sodium ion occupy the octahedral voids, and the octahedral voids are present in the center of the cubic unit cell as well as at the center of the edges. So here, this is the structure of sodium chloride. So these are chloride ion, relatively bigger in size than sodium ion. So chloride ion, it is undergoing FCC unit shell. It is undergoing cubic closed packing. So it is giving an FCC unit cell. Here you can see this is chloride ion, this is chloride ion, this is chloride ion, this is chloride ion at the corner, and chloride ion is at the center of the face. This is at the center of the top face, this is the center of this face. And the sodium ion are occupying all octahedral void, and the octahedral void is a void between 6 units at the 6 corners of an octahedral. So this is the center of the cubic unit cell, and this is an octahedral void, and this can be shown in this picture. You see, this is an octahedral if you join these atoms. 1, 2, 3, 4, 4 atoms in the same plane, 1 atom at the top and 1 atom at the bottom. So there are 6 atoms at the 6 corners of the octahedral, and sodium ion is at the center. That means sodium ion is occupying the octahedral void. So here the coordination number of sodium ion will be 6, as well as the coordination number of chloride ion will be also 6, because each sodium ion is octahedrally surrounded by 6 chloride ion, and each chloride ion is also surrounded by 6 sodium ion. So the coordination number in sodium chloride is 6 for sodium ion and 6 for chloride ion. Then we have this cesium chloride structure. So in cesium chloride, chloride ion, it is undergoing cubic, it is undergoing, it is a BCC type of unit cell, where chloride ion are occupying the corners of a cubic unit cell, and cesium ion is at the center of the cubic unit cell. So the coordination number of cesium will be 8. 1, 2, 3, 4, 5, 6, 7, 8. So cesium ion will have 8 chloride ion, and each chloride ion also have cesium ion around it. Then this is interesting, that is the zinc blende structure. So in zinc blende structure, the sulfide ion, which is relatively bigger in size than zinc ion, it undergoes cubic close packing. So sulfide ion is undergoing cubic close packing, so it is giving a FCC unit cell, and half of the tetrahedral holes will be occupied by zinc ion. So in an FCC unit cell, there are 4 octahedral voids and there are 8 tetrahedral voids. So in sodium chloride, we have seen that chloride ion is occupying, it is undergoing cubic close packing, so it is giving an FCC unit cell, and all sodium ions are occupying the octahedral voids. And in zinc sulfide, sulfide ion is undergoing cubic close packing, so it is giving an FCC unit cell, and there are 8 tetrahedral voids, and out of this 8 tetrahedral void, half of them are occupied. That means 4 tetrahedral voids are occupying. These are the tetrahedral voids, and there are 4 zinc ion per unit cell. 1, 2, 3, 4. So I'm again repeating that in an FCC unit cell, there are 4 octahedral voids and there are 8 tetrahedral voids. So in sodium chloride, all the octahedral voids are occupied by sodium ion, and in zinc sulfide, sulfide ion is undergoing cubic close packing, so it is giving FCC unit cell. So these are the black dots, they represent sulfide ion, and this sulfide ion, they form an FCC unit cell, which are at the corners and at the center of the faces, and half of the tetrahedral voids or half of the tetrahedral holes, that means 4 tetrahedral holes per FCC unit cell, will be occupied by zinc. Then we have another calcium fluoride structure, that is also called the fluoride structure. So here what is happening? Calcium ion, it is undergoing cubic close packing, because calcium is bigger in size than fluoride ion. Calcium ion Ca plus 2, it is 2, 8, 8. Fluoride ion, it is 2, 8. So calcium ion is having 3 shells, fluoride ion is having 2 shells complete. So calcium ion is slightly bigger than fluoride ion. So calcium ion is undergoing cubic close packing, and it is giving rise to an FCC unit cell. So these black dots are calcium ion. They are forming an FCC unit cell. Here you can see 1, 2, 3, 4. 4 units at the corner. 4 units will be here at the corner, and each face is having 1 unit at the center. This is the calcium, and this is calcium. And in calcium fluoride, all the tetrahedral voids, that means all the 8 tetrahedral holes, are occupied by fluoride. So this is what I want to speak to you about. So I have discussed you about three types of ionic crystal. One is the rock salt structure, the other one is the zinc sulfide structure, and the other one is the calcium fluoride structure, or it is the fluoride structure. So what we have learned that in ionic crystal, either the cation or anion, they will undergo cubic close packing, and the oppositely ions will be placed in the holes, which may be in the octahedral hole or in the tetrahedral hole. So I hope my lectures upon solid state in 4 parts, part 1, part 2, part 3, part 4, I could throw light upon the solid state. And in coming years, I will be uploading more such videos. And if you like this video, please subscribe it, then only you will get timely updates. So I will be with a promise that I will meet you again in coming years. So now it's goodbye for me. Have a good day. Thank you.